Right now, your smartphone contains more computing power than NASA had when it sent humans to the moon. Yet there are problems so fundamentally complex that every computer on Earth, running simultaneously for billions of years, could not solve them. Not because computers are slow, but because the problems themselves exist in a dimension of complexity that binary machines are structurally incapable of reaching. Quantum computers change that, not by being faster versions of what we already have, but by operating according to an entirely different set of rules, rules that the universe itself runs on at its most fundamental level. To understand why that matters, we need to start somewhere unexpected, with a coin. Flip a coin 20 times, record each result. The odds that any other person on Earth produces that exact sequence of heads and tails is roughly 1 in a million. Now flip it 100 times. The number of possible sequences exceeds the number of atoms in a visible star. Push it to 266 flips, and the total number of possible sequences surpasses the most commonly cited estimates for the number of atoms in the entire observable universe. 2 to the power of 266 is a number so large that if every person on Earth used a computer capable of counting 10 billion sequences per second, it would still take longer than the age of the universe to list them all. Expand that to 10 billion planets like Earth, each with 10 billion people, each with those same computers, still not enough. Add 10 billion galaxies, 10 billion universes, and you still fall short. This is not a quirk of mathematics. It is a statement about the nature of complexity itself. The universe is not simple. We just evolved to think in patterns because it helped us survive, not because it reflects the actual structure of reality. This tension between human cognition and cosmic complexity sits at the heart of why quantum computing exists and why it represents something genuinely different in the history of human technology. To understand what quantum computers actually are, we need to understand what classical computers actually do and where they break down. Every classical computer, from a pocket calculator to the world's fastest supercomputer, operates on bits. A bit is a switch. It is either off, representing 0, or on, representing 1. Everything your computer does, every email, every video, every financial transaction, every weather forecast, is the result of billions of these switches flipping in precise, predetermined sequences. The operations are deterministic, step by step, sequential, one state at a time. When you take a digital photograph, the image is stored as millions of pixels, each encoded in binary. When a meteorological system models a storm, it converts temperature, air pressure, humidity, and wind speed into binary representations and processes them numerically, one calculation after another. These are tasks classical computers handle beautifully, precisely because they reduce everything to a manageable linear sequence. But some problems refuse to stay linear. Consider a molecule. Even a relatively simple molecule like caffeine contains dozens of atoms, and those atoms interact quantum mechanically, meaning their electrons exist in complex, overlapping states that cannot be captured in binary. To simulate caffeine's behavior accurately on a classical computer, you would need to track every possible quantum interaction between every electron in every atom simultaneously. For caffeine, that is already computationally punishing. For larger molecules, proteins, for instance, it becomes effectively impossible. The number of states you need to track grows exponentially with every additional atom, and exponential growth defeats even the fastest classical hardware. This is not an engineering limitation that better processors will solve. It is a mathematical wall. Classical computers are built for a certain class of problems, and quantum mechanical simulation is simply outside that class. The same issue appears in cryptography, optimization, drug discovery, materials science, and dozens of other fields. The problems are not difficult because our computers are too slow. They are difficult because the structure of the problem itself demands a type of computation that binary architecture cannot provide. The idea that a different computational architecture might exist was first articulated seriously in 1980, when a physicist named Paul Benioff proposed a theoretical machine that operated not on classical bits, but on units of quantum information. He called it a quantum Turing machine. At the time, it was almost entirely abstract, a thought experiment dressed in mathematical formalism. Classical computers were advancing rapidly, and the practical need for something fundamentally different was not yet obvious. That changed when physicists began seriously attempting to simulate quantum systems on classical hardware. The problem became clear almost immediately. You cannot use a system that operates one step at a time to accurately model a system that operates in multiple states simultaneously. The computational cost grows so fast that even modest quantum systems overwhelm classical machines entirely. Richard Feynman, one of the most creative physicists of the 20th century, articulated this directly. If you want to simulate nature, he argued, you need a machine that behaves like nature. A machine built on the same quantum mechanical rules that govern particles, atoms, and interactions at the smallest scales. Yuri Manin reached a similar conclusion independently. Both men were pointing toward the same idea, that the universe computes, and if we want to harness that computational power, we need to build machines that speak the universe's language. That language is quantum mechanics. The fundamental unit of quantum computing is the qubit. Unlike a classical bit, which must be either 0 or 1, a qubit can exist in a superposition of both states simultaneously. This is not a metaphor or an approximation. It is a direct consequence of quantum mechanics. The same physics that describes how electrons behave around atomic nuclei and how photons travel through space. To understand superposition intuitively, consider a coin in flight. Before it lands, it is not secretly either heads or tails, and you simply do not know which. According to quantum mechanics, it genuinely exists in a combination of both possibilities. The state only resolves collapses into a definite outcome when a measurement is made. Qubits behave the same way. A single qubit holds both 0 and 1 simultaneously until it is measured. A system of 2 qubits holds 4 states simultaneously. 10 qubits hold 1024 states simultaneously. The scaling is exponential. N qubits hold 2 to the power of n states at once. With 300 qubits, a quantum computer can represent more simultaneous states than there are particles in the observable universe. That is not a performance benchmark. It is a statement about the nature of information itself. Classical computers process one state at a time and simulate parallel processing. Quantum computers actually exist in all those states at once and process them in parallel at the physical level. But superposition alone does not make a quantum computer useful. The second principal entanglement is where things become genuinely extraordinary. When 2 qubits become entangled, they enter a shared quantum state. Measuring one qubit instantly determines the state of the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance and spent years trying to explain it away. Decades of increasingly precise experiments have confirmed that it is real, fundamental, and not reducible to any hidden classical mechanism. The entanglement is genuine. The correlation is instantaneous. In a quantum computer, entanglement allows qubits to coordinate. The state of one qubit is mathematically linked to the states of others in a way that classical bits simply cannot replicate. This interconnection means that when a quantum computer processes information, the qubits are not just individually in superposition, they are collectively entangled, forming a computational fabric of interlocked possibilities. The third principle is quantum interference. This is the mechanism by which quantum algorithms actually produce useful results rather than just generating noise. In quantum mechanics, probability amplitudes, the mathematical quantities describing the likelihood of different outcomes, can add together or cancel out, just like waves on the surface of water. Quantum algorithms are designed to make the probability amplitudes corresponding to wrong answers cancel each other out, while the amplitudes corresponding to correct answers reinforce each other. The measurement then collapses the system into a state that is overwhelmingly likely to be the right answer. This is why quantum computing is not simply about brute force. It is about orchestrating interference patterns across exponentially large state spaces, so that useful information emerges naturally from the quantum calculation. The encryption that protects your credit card number when you shop online relies on a mathematical problem called integer factorization. The idea is straightforward. It is easy to multiply two large prime numbers together to produce an even larger number. But reversing that process, starting with the large number and finding the two primes that produced it, is computationally catastrophic for classical machines. To see why, consider how RSA encryption works. When you submit your payment information to an online retailer, your browser encrypts that data using the retailer's public key, a very large number that is freely available. The encryption locks your data in a mathematical box that can only be unlocked using the corresponding private key, which the retailer holds secretly. The security of this system depends entirely on the fact that factoring the public key into its component primes would take a classical computer an impractical amount of time. The largest RSA number successfully factored using classical methods required the equivalent of 2,000 years of distributed computing effort across multiple machines. Larger keys are proportionally harder. Current encryption standards use keys of 2048 bits, and factoring a 2048-bit number with classical hardware would take longer than the current age of the universe. In 1994, a mathematician named Peter Shor developed an algorithm that runs on a quantum computer and factors large numbers in polynomial time, meaning the computational cost grows manageably rather than exponentially as the numbers get larger. A quantum computer running Shor's algorithm could crack 2048-bit RSA encryption in hours. This is not a hypothetical academic concern. It is a practical deadline that cybersecurity experts around the world are actively working against. The transition to quantum-resistant encryption protocols is already underway, driven by the recognition that sufficiently powerful quantum computers are a matter of when, not if. Quantum key distribution offers an alternative approach to secure communication that does not depend on computational difficulty at all. Instead, it uses the laws of physics directly. The protocol, developed by Charles Bennett and Gilles Brassard in 1984, works like this. A sender transmits information encoded in the quantum states of individual photons. Because measuring a quantum state disturbs it, any eavesdropper attempting to intercept the photons necessarily leaves a detectable trace. The two parties can then verify whether their communication was compromised by comparing a small sample of their results. If the comparison shows no discrepancies, they know the key is secure and can use it to encrypt their messages. If discrepancies appear, they know someone was listening and discard the key entirely. The security of quantum key distribution does not rest on mathematical assumptions. It rests on the structure of quantum mechanics itself. No future advance in computing power can undermine it, because the protection comes from the physical impossibility of measuring a quantum state without disturbing it, not from the difficulty of solving a mathematical problem. Quantum key distribution is not theoretical, it is operational. Financial institutions, government agencies, and defense organizations in multiple countries are already using it to protect their most sensitive communications. Optimization is another domain where quantum computing offers capabilities that classical systems cannot match. Consider the challenge of routing a delivery fleet across a city with hundreds of destinations. The number of possible routes grows factorially with the number of stops, meaning it grows faster than any polynomial and faster than almost any exponential. Classical computers address this with heuristics, intelligent shortcuts that find good solutions without guaranteeing the best one. Quantum algorithms can explore the full solution space in ways classical heuristics cannot, finding true optima rather than approximations. The same logic applies to airline scheduling, traffic management, logistics networks, portfolio optimization in finance, and the design of complex industrial processes. Each of these domains involves enormous combinatorial spaces, where the classical approach of finding approximately good solutions leaves measurable inefficiency on the table. Quantum optimization does not just save time, it unlocks genuinely better outcomes that classical machines are structurally prevented from finding. Drug discovery is perhaps the most consequential near-term application. Designing a new pharmaceutical compound requires understanding how that compound will interact with specific proteins in the human body. Proteins are large, complex molecules whose behavior is fundamentally quantum mechanical. Their three-dimensional structure determines their function, and that structure is the result of a process called protein, folding the way a chain of amino acids spontaneously arranges itself into a precise three-dimensional shape. Predicting how a given protein will fold from its amino acid sequence is one of the hardest problems in biology. Artificial intelligence, particularly DeepMind's AlphaFold system, has made remarkable progress on this problem by learning from enormous databases of known protein structures. But simulating the full quantum mechanical behavior of novel molecules, not just predicting their shapes, but modeling how they will interact at the quantum level with drug candidates, remains beyond what classical machines, AI, can currently handle. Quantum computers are uniquely suited to this problem because molecular behavior is quantum mechanical. They do not need to approximate quantum interactions. They can model them directly. The implications for medicine are significant. Faster development of new drugs, better understanding of disease mechanisms, and the ability to design molecules with specific properties that classical computational methods can only guess at. Google's Willow quantum processor, announced in late 2024, completed a benchmark computation in under 5 minutes that would have required the world's fastest classical supercomputer longer than the current age of the universe. This particular benchmark was specifically designed to test quantum computational ability rather than to solve an immediately practical problem. But the underlying advanced beta error correction that improves as more qubits are added is directly relevant to everything quantum computers might eventually accomplish. Error correction is the central engineering challenge in quantum computing. Qubits are extraordinarily fragile. They exist in superposition only as long as they remain isolated from their environment. Thermal vibrations, electromagnetic interference, even cosmic rays can cause a qubit to decohere, meaning its quantum state collapses prematurely, destroying the computation. This is called decoherence, and it is not an engineering problem that can be solved with better materials alone. It is a fundamental feature of the relationship between quantum systems and the environment. The solution is quantum error correction, using additional qubits to continuously monitor and correct the errors that inevitably accumulate in the computational qubits. In current systems, the overhead is substantial. A computation that theoretically requires 1,000 logical qubits might demand millions of physical qubits when error correction is factored in. Maintaining those qubits requires cooling them to temperatures near absolute zero colder than outer space and isolating them in electromagnetic shielding. This is why the Willow processor's breakthrough in error correction matters so much. For the first time, Google demonstrated that as more qubits were added to the system, the error rate went down rather than up. This is the threshold behavior that quantum error correction theorists have long predicted is necessary for scalable quantum computing. Crossing that threshold does not mean the engineering problems are solved. but it means the path to solving them is now demonstrably open. Current quantum computers are best understood as highly specialized prototypes. Google's Sycamore processor, Rigetti's Aspen M platform, IBM's quantum systems, and the photonic processors developed by companies like PsiQuantum are each designed to explore different aspects of quantum computational architecture. Each has different strengths and weaknesses, different qubit technologies, and different approaches to error mitigation. None of them is yet a general-purpose quantum computer capable of outperforming classical hardware on practically important problems at scale. For factoring the encryption keys that protect current internet security, a quantum computer would need millions of stable, error-corrected, logical qubits. We currently have hundreds of noisy physical qubits. The gap is large, but it is not infinite, and it is closing. What makes quantum computing philosophically interesting, not just technologically impressive, is the nature of what quantum computers reveal about the relationship between computation and reality. Physicist Seth Lloyd, a professor at MIT, proposed that the universe itself might be understood as a quantum computer, not in a metaphorical sense, but as a precise description of what the universe is doing at every moment. Every interaction between particles, every collision, every decay, every photon absorbed or emitted is a quantum mechanical event that processes information according to fixed rules. The evolution of the universe, from the Big Bang to the present moment, can be understood as a single, unimaginably vast computation playing out across space and time. This is not mysticism. It is a natural consequence of taking quantum mechanics seriously as a description of physical reality. Quantum mechanics is a theory about information, about what can be known, what is determined, and what remains in superposition until measured. If the universe operates according to quantum mechanical laws, and it does, then the universe is processing quantum information at every scale, from the interactions of quarks inside atomic nuclei to the large-scale structure of galaxy clusters. In this framework, a quantum computer is not something separate from the universe running computations about it. It is a small, carefully controlled piece of the universe, running computations that mirror the universe's own processes. When a quantum computer simulates a molecule, it is using quantum mechanical processes to model quantum mechanical processes. The simulation and the reality speak the same mathematical language. This perspective became dramatically concrete in late 2022, when physicists used Google's Sycamore quantum processor to simulate the behavior of a wormhole. To be precise about what this experiment did and did not accomplish, no physical wormhole was created. No tunnel through spacetime connecting distant points actually existed inside the processor. What the researchers did was encode quantum states into the processor and manipulate them in a way that reproduced the mathematical dynamics, describing how quantum information would travel through a theoretical wormhole as described by equations from quantum gravity. The theoretical framework they used was the holographic principle, a profound idea in theoretical physics, suggesting that the physics of a higher dimensional space can be completely described by information encoded on its lower dimensional boundary, much as a three-dimensional scene can be encoded in a two-dimensional hologram. Applied to gravity, this principle suggests that the geometry of spacetime, including exotic structures like wormholes, might be understood as emerging from quantum information relationships. What the Sycamore experiment showed was that quantum entanglement between two subsystems of the processor could produce exactly the signal that would be expected if quantum information had traveled through a wormhole connecting those subsystems. The experiment did not create a wormhole, but it demonstrated that the mathematical description of wormholes and the mathematical description of quantum entanglement are deeply, perhaps fundamentally, connected. This connection is at the frontier of theoretical physics. The relationship between quantum mechanics and general relativity, the theory that describes gravity and the geometry of spacetime remains one of the deepest unresolved problems in all of science. Quantum mechanics and general relativity are each extraordinarily successful in their own domains, but their mathematical structures are incompatible. Unifying them into a single coherent theory of quantum gravity is the central, unsolved problem of fundamental physics. The wormhole simulation on Sycamore did not solve that problem, but it provided a concrete, experimental demonstration of ideas connecting entanglement to spacetime geometry. It showed that quantum computers are not just tools for solving practical problems. They are instruments capable of probing the deepest questions about the structure of reality. If quantum computers can simulate wormhole dynamics, the natural question is, what else can they simulate? The answer, in principle, is anything that obeys quantum mechanical laws. That includes the behavior of matter in the extreme conditions near black holes, the dynamics of the early universe in the moments after the Big Bang, the properties of quantum fields in the vacuum of space, and the detailed structure of any material or chemical system that humans might want to design or understand. This is why theoretical physicists are genuinely excited about quantum computing in a way that goes beyond practical applications. A sufficiently powerful quantum computer would be a universal quantum simulator, a machine capable of modeling any quantum system with full physical fidelity. For the first time in history, we would have a tool capable of exploring the quantum mechanical reality of the universe, not just through abstract mathematics, but through direct computation. There is, however, an important epistemological point lurking underneath all of this, and it is worth dwelling on. Return to the coin flip thought experiment. When each of those 266 flips is truly independent, when the outcome of each flip has no relationship to any other flip, the problem of counting all possible sequences is merely enormous. It is bounded by a number that is unimaginably large, but still finite and well-defined. That is the tractable case, the one where independence allows us to use probability theory, where the combinatorics are well understood even if computationally prohibitive. But consider the harder version. What if each flip's outcome depends on all previous flips in some complex, entangled way? What if the coin has, in a manner of speaking, a memory? Now you are not just dealing with an enormous number of possible sequences. You are dealing with an enormous number of possible interdependency structures, each generating its own set of possible sequences. The complexity is not just exponential. It is recursively exponential in a way that resists even quantum computational approaches. This is a precise description of what makes genuinely complex systems, consciousness, ecosystems, social dynamics, turbulent fluid flow so difficult to model. It is not merely that they involve many variables. It is that the variables are interconnected in ways that compound complexity non-linearly. Every classical computer ever built has dealt with this by restricting the class of problems it attempts to solve to those where the interdependencies can be simplified or ignored. Computers are, in a deep sense, instruments for managing tractable slices of an intractable reality. Quantum computers expand the boundary of tractability significantly. They can handle classes of problems that are permanently beyond classical reach, but they do not eliminate the boundary. A quantum computer is still a device that we design to solve specific problems within specific mathematical frameworks. The universe's full complexity, the actual interdependency structure of all physical processes across all scales, is not something any machine will ever fully capture. This is not a limitation unique to technology. It is a feature of knowledge itself. Our scientific models, however sophisticated, are always representations, maps, not territories. The Schrödinger equation, the mathematical backbone of quantum mechanics, is extraordinarily precise and experimentally confirmed to a degree unmatched by any other scientific theory. It tells us how quantum states evolve, how probabilities are distributed, how particles interact. But the equation is a human construction, a compressed, elegant representation of something that the universe simply does, without reference to any equation at all. When we build a quantum computer, we are building a machine that implements certain quantum mechanical processes in a controlled way to perform computation. We are using the universe's own language to ask the universe specific questions. The answers we get are genuine and often remarkable, but they are answers to the questions we are capable of asking, shaped by the frameworks we have developed, the algorithms we have designed, and the problems we have learned to recognize. This is not a counsel of despair. It is a clarification of what progress in quantum computing actually means. Each advance better qubits, better error correction, better algorithms, better understanding of quantum algorithms applicable to real-world problems, genuinely expands what is knowable. The simulation of wormhole dynamics on Sycamore was not a stunt. It was a demonstration that the boundary of knowable things has moved. The historical development of quantum computing parallels in interesting ways the history of classical computing. Early computers were enormous, fragile, expensive, and capable only of tasks that seem trivial by today's standards. They ran in specialized facilities, required teams of trained operators, and broke down frequently. The transition from those machines to the devices that now fit in your pocket took several decades and required not just engineering advances, but fundamental conceptual progress in algorithms, programming languages, operating systems, and the mathematics of information. Quantum computing is currently somewhere in the early phase of that arc. The machines are large, fragile, expensive, and capable primarily of demonstrating proof-of-concept computations that approach but do not yet exceed classical hardware on practically important problems. The engineering challenges decoherence, error correction, qubit connectivity, precise control at the quantum level are formidable. Progress is real but gradual. The conceptual work is also incomplete. Classical computing benefited from decades of work in algorithm development, identifying classes of problems that computers could solve efficiently, and developing the specific step-by-step procedures for solving them. Quantum algorithm development is a younger field. We know that quantum algorithms offer exponential advantages over classical methods for certain specific problem types factoring, certain simulation problems, certain optimization problems. For many other problem types, the quantum advantage is less clear, and in some cases, non-existent. This is why the relationship between quantum computing and artificial intelligence is more nuanced than popular coverage suggests. AI, particularly deep learning systems, has made extraordinary progress on problems that were previously thought to require more fundamental mathematical breakthroughs, including protein folding prediction, which AlphaFold addressed with stunning accuracy. In some domains, sufficiently large AI systems trained on sufficiently large datasets can approximate results that theorists once assumed would require quantum computation. This does not mean AI has made quantum computing obsolete. The boundary between what AI can handle and what requires quantum computation is not fixed. As problems grow in complexity, as the molecules to be simulated grow larger, as the optimization spaces grow wider, as the physical systems to be modeled grow more quantum mechanical, in character, AI approaches, trained on classical hardware, hit their own walls. The complementarity between classical AI and quantum computation is probably the most accurate framing. Each is the right tool for a different class of problems, and the most powerful approaches will likely combine both. Quantum machine learning is already an active research area. Algorithms that use quantum superposition to process and analyze high-dimensional datasets may offer advantages over purely classical machine learning for specific applications. The full scope of those advantages is not yet understood, but the theoretical groundwork is being developed across dozens of research groups worldwide. What remains genuinely unknown is the timeline. building a quantum computer with millions of error-corrected logical qubits the scale needed for practically important applications like cracking current encryption or simulating large biological molecules requires solving engineering problems that are currently unsolved and may require conceptual breakthroughs that have not yet occurred. Optimistic estimates from leading researchers suggest this could be achievable within 1 to 2 decades. More conservative estimates place it further out. The honest answer is that no one knows. What is clear is the direction. Qubit counts are increasing, error rates are decreasing. New quantum hardware architectures, including superconducting qubits, trapped ion qubits, photonic qubits, and topological qubits, are being developed in parallel, each with different trade-offs between stability, connectivity, and scalability. International investment in quantum computing research from governments, corporations, and universities is at an all-time high. The competitive pressure to achieve quantum advantage on practically important problems is intense and growing. The societal implications of mature quantum computing extend well beyond cryptography and drug discovery. Climate modeling requires simulating the quantum mechanical interactions of molecules in the atmosphere and oceans at a level of detail that classical computers cannot achieve. Material science breakthroughs, new superconductors, new battery materials, new catalysts for industrial chemistry depend on understanding quantum mechanical behavior at the atomic scale. Financial modeling, traffic management, supply chain optimization, and the design of complex engineered systems all involve optimization problems where quantum advantage could translate directly into efficiency gains measurable in energy saved, time reduced, and resources preserved. The transition to a post-quantum cryptographic infrastructure is already legally mandated in some jurisdictions. The National Institute of Standards and Technology in the United States finalized quantum-resistant cryptographic standards in 2024 after a multi-year evaluation process involving cryptographers from around the world. The migration of existing digital infrastructure to these new standards is a massive engineering and logistical undertaking that will take years to complete. The urgency is driven not just by the expected arrival of cryptographically relevant quantum computers, but by the possibility of harvest now decrypt later attacks. Adversaries recording encrypted communications today and storing them for decryption once quantum hardware becomes capable. The question of who achieves large-scale quantum computing first and what they do with it is genuinely consequential for global security and economic power. This is not a theoretical concern. It is being treated as a strategic priority by national governments on every continent. And yet, for all the practical stakes and engineering challenges, there is something that the science of quantum computing keeps pointing back toward, something more fundamental than any application. The fact that a quantum computer can simulate a wormhole is not just a remarkable engineering achievement. It is a window into a question that physicists have been circling for a century. What is space? What is time? And what is the relationship between information and physical reality? The holographic principle, which the wormhole experiment was designed to test, suggests that space itself might be a derived quantity, something that emerges from underlying quantum information, relationships, rather than existing as a fundamental background stage on which events play out. If that is correct, then the geometry of the universe, the fabric of spacetime, is not the ground floor of reality. Quantum information is. This idea, if true, would represent a conceptual revolution more profound than anything since the development of general relativity and quantum mechanics themselves. It would mean that space is not where things happen. Space is what happens when quantum information becomes organized in certain ways. Gravity would not be a force acting across space. It would be a consequence of quantum entanglement structures. The theoretical evidence for this view, coming from string theory, loop quantum gravity, and the study of quantum gravity in anti-de Sitter space, is fragmentary and contested. No one claims it is established. But the fact that a quantum computer running on a table in a Google laboratory can produce dynamics consistent with wormhole behavior is a concrete step toward testing these ideas experimentally rather than just arguing about them mathematically. This is the frontier. Not just faster computers, not just better drugs and more efficient delivery routes. The frontier is a new way of understanding what reality is made of, built on the recognition that information, quantum information, may be more fundamental than space, time, or matter. We are at the beginning of that investigation. The quantum computers that exist today are rudimentary instruments by the standards of what will eventually be possible. But rudimentary instruments at the right moment in history have a way of changing everything they touch. The telescope was a simple lens arrangement when Galileo turned it toward Jupiter. The apparatus that Thomson used to discover the electron was a glass tube and some metal plates. The machines that first implemented Turing's computational ideas were enormous, expensive, and capable of almost nothing by modern standards. What quantum computers are building toward is an entirely new relationship between human understanding and physical reality. Not just a new tool for solving old problems, but a new way of asking questions that could not even be formulated before. The science is real. The challenges are real. The uncertainty about timing and ultimate capability is honest. What is not uncertain is that the principles are correct, the mathematics is sound, and the universe, which has been computing quantum mechanically since the first moments after the Big Bang, does not need our permission to keep doing so. We are learning to ask it questions in its own language. The answers, when they come, will be interesting. If you find yourself wanting to follow this story as it develops the engineering advances, the algorithm breakthroughs, the deepening understanding of what quantum computation reveals about physical reality, consider subscribing so you do not miss what comes next. The science moves fast, and it is worth keeping up with. Research into fault-tolerant quantum computing is ongoing at laboratories across the world. The specific engineering targets are known: millions of physical qubits with error rates below certain thresholds, quantum interconnects capable of linking separate processors, and control systems precise enough to manipulate individual qubits without disturbing their neighbors. Progress on each of these fronts is measured and published regularly. Theoretically, the open questions are even larger. The precise relationship between entanglement and spacetime geometry is not understood. The conditions under which quantum computers could provide advantage for machine learning problems are still being mapped out. The full landscape of quantum algorithms, what they can and cannot efficiently solve, remains only partially explored. The question of whether consciousness, biological processes, or economic systems have any genuinely quantum mechanical aspects that affect their behavior is debated and unresolved. What is known is that quantum mechanics is the correct description of physical reality at the fundamental level, that quantum computers implement those principles in a controlled and useful way, and that the boundary of what is computationally tractable is not fixed. It has moved before, and it is moving again. The universe has been running its computation since the beginning. We are only now learning how to read it. To truly appreciate what quantum computing represents, it helps to understand the history of how we arrived at quantum mechanics in the first place, because the path was not a steady march of progress. It was a series of conceptual collisions that forced physicists to abandon deeply held assumptions about the nature of reality, one by one. The story begins in the final years of the 19th century, when physics appeared to be nearly complete. Newtonian mechanics described the motion of everything from cannonballs to planets with extraordinary precision. Maxwell's equations unified electricity, magnetism, and light into a single, elegant framework. Thermodynamics provided rigorous rules for heat, and energy. The major problems seemed solved. Some physicists reportedly suggested that the young generation should consider other fields because there was little left to discover. Then, in 1900, a physicist named Max Planck was trying to explain the spectrum of light emitted by hot objects, a phenomenon called blackbody radiation. The existing theories predicted that hot objects should emit infinite amounts of energy at short wavelengths, a prediction so obviously wrong that it was called the ultraviolet catastrophe. Planck found that he could fix the math by assuming that energy was not continuous but came in discrete packets, what he called quanta. He did not believe this was physically real. He thought it was a mathematical trick that happened to produce the right numbers. He was wrong about that. The packets are real. Albert Einstein built on Planck's idea in 1905 to explain the photoelectric effect, the observation that shining light on certain metals ejects electrons, but only if the light is above a certain frequency, regardless of intensity. Einstein proposed that light itself consists of discrete particles, later called photons, each carrying an energy proportional to its frequency. This explained the photoelectric effect perfectly and earned Einstein the Nobel Prize in Physics in 1921. It also meant that light was simultaneously a wave and a particle, a fact that defied every classical intuition about what waves and particles are. Niels Bohr applied the quantum idea to the structure of atoms in 1913. Classical physics predicted that electrons orbiting atomic nuclei should continuously radiate energy and spiral inward, causing all atoms to collapse in a fraction of a second. Obviously, atoms do not do this. Bohr proposed that electrons could only occupy certain discrete orbits, each corresponding to a specific energy level, and that they could only emit or absorb energy by jumping between orbits. This was arbitrary and inexplicable within any framework that existed at the time, but it produced predictions that matched experimental observations with remarkable precision. The deeper theoretical framework came in the 1920s through the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Max Born. Heisenberg formulated quantum mechanics in terms of matrices, abstract mathematical arrays encoding the observable quantities of a system and their relationships. Schrödinger reformulated the same physics as a wave equation, the equation that appears at the opening of the source material for this script, describing how the quantum state of a system evolves through time. Dirac synthesized the two approaches and extended quantum mechanics to be compatible with special relativity, leading to the prediction of antimatter. Max Born provided the probabilistic interpretation. The wave function does not describe a physical wave in space. It encodes probability amplitudes, mathematical quantities whose squared magnitudes give the probability of observing specific outcomes when a measurement is made. This was the interpretation that Einstein spent decades resisting. The idea that physics at the fundamental level is not deterministic, that there is no fact of the matter about the position of an electron before it is measured, only probabilities struck him as deeply unsatisfying. He famously insisted that God does not play dice. The experimental evidence overwhelmingly supports Born's interpretation. Every test of quantum mechanics ever conducted has confirmed its predictions. The theory is not just approximately correct. It is correct to a degree of precision that no other physical theory has achieved. The anomalous magnetic moment of the electron, a quantum mechanical quantity, has been measured experimentally and calculated theoretically to better than 1 part in a trillion, and the results agree. If quantum mechanics is wrong, the error is smaller than anything current technology can detect. The Heisenberg uncertainty principle is often misunderstood as a statement about measurement limitations, as though the problem is that measuring one quantity disturbs another. It is actually a deeper statement about the structure of reality. Certain pairs of physical quantities, position and momentum, energy and time, are fundamentally complementary in quantum mechanics. They do not have simultaneously definite values. This is not because we lack precision. It is because the definiteness of one is mathematically incompatible with the definiteness of the other. The uncertainty is intrinsic to the quantum state, not imposed by the act of measurement. This has direct consequences for quantum computing. The uncertainty principle means that quantum information has properties that classical information does not. It cannot be copied perfectly, a result known as the no-cloning theorem. If someone intercepts a quantum communication and tries to copy the quantum states to measure them covertly, the copying itself introduces detectable errors. This is the foundation of quantum key distribution security. The no-cloning theorem also shapes quantum error correction. You cannot simply copy a qubit state to back it up the way you back up classical data. Quantum error correction works instead through entanglement, encoding the logical qubit state across multiple physical qubits in a way that allows errors to be detected and corrected without ever directly measuring the logical qubit state. Understanding why this works requires understanding what entanglement actually is at a mathematical level, not just as a metaphor. When two particles become entangled, their quantum states cannot be described independently. Instead, their combined state is described by a single quantum state that spans both particles simultaneously. Measuring one particle and finding it in a particular state does not cause the other particle to become that state. Rather, the measurement reveals information about the joint state that was always there, a correlation that existed in the entangled state before any measurement was made. John Bell, an Irish physicist working at CERN in the 1960s, proved mathematically that if the correlations between entangled particles were due to hidden local variables, some classical mechanism we had not yet discovered, they would have to satisfy certain inequalities. He showed what the maximum strength of correlations could be if the universe were described by any local realistic theory. Experiments testing these inequalities, beginning with those conducted by Alain Aspect and colleagues in 1982, and continuing with increasingly precise tests through the following decades, have consistently violated Bell's inequalities. The correlations in quantum mechanics are stronger than any local realistic theory can produce. This means entanglement is not a form of classical correlation that we happen not to understand yet. It is a genuinely non-classical phenomenon with no classical analogue. The two particles in an entangled pair are not like two gloves, where knowing one is left-handed tells you the other is right-handed. The information was always there and independent. Entangled particles exist in a genuinely joint state where the properties of each particle only become definite in relationship to the measurement of the other. Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics in 2022 for their experimental work on entanglement and violations of Bell inequalities. The Nobel Committee's citation explicitly noted the importance of their work in enabling quantum information technologies, including quantum computing and quantum cryptography. This recognition reflects the maturity of the field. What was once a philosophical curiosity about the foundations of physics has become the basis of a technological revolution. The connection between quantum mechanics and information theory runs deep. Claude Shannon developed classical information theory in 1948, establishing the mathematical foundations for how information can be quantified, transmitted, and compressed. His central insight was that information is physical. It has to be encoded in some physical system and transmitted through some physical channel. And the properties of those physical systems and channels determine what can and cannot be communicated. Quantum information theory extends Shannon's framework to quantum mechanical systems. Quantum bits, qubits, obey different rules than classical bits. They cannot be perfectly copied. They can exist in superposition. They can be entangled. These properties create both new limitations and new capabilities. The no-cloning theorem limits what can be done with quantum information in ways that have no classical analogue, but superposition and entanglement enable capabilities like quantum teleportation and quantum key distribution that are impossible with classical information. Quantum teleportation is frequently misunderstood, so it is worth explaining carefully. The name is genuinely misleading. Quantum teleportation does not transport matter through space instantaneously. What it does is transfer a quantum state, the complete quantum mechanical description of a particle, from one location to another using an entangled pair shared between sender and receiver along with a classical communication channel. The process works as follows. The sender has a particle in an unknown quantum state that they want to transmit. They have previously shared an entangled particle pair with the receiver, one particle at the sender's location, one at the receiver's. The sender performs a measurement involving their particle and the particle they want to teleport, then transmits the classical result of that measurement to the receiver through an ordinary communication channel. The receiver uses that classical information to perform a specific operation on their particle from the entangled pair. After this operation, the receiver's particle is in exactly the same quantum state that the sender's particle was in before the measurement. Crucially, the quantum state of the original particle is destroyed in the process, consistent with the no-cloning theorem. The state is not copied, it is moved. And the transfer cannot happen faster than the classical communication that carries the measurement result, so quantum teleportation does not violate the speed of light. It does demonstrate that quantum states can be transferred between particles without directly sending the particles themselves, which has practical implications for quantum communication networks. Quantum network systems linking multiple quantum computers or quantum communication nodes through quantum channels are an active area of research and early deployment. A quantum internet, in which quantum states can be reliably transmitted between distant nodes, would enable communication security fundamentally guaranteed by physics and distributed quantum computation across geographically separated processors. Several countries have established testbed quantum networks, and there is ongoing international effort to develop the repeaters and memory systems needed to extend quantum networks to global scale. The Chinese satellite Micius demonstrated satellite-based quantum key distribution over distances greater than 1,000 kilometers in 2017, a landmark achievement in quantum communication. European projects, including the Quantum Internet Alliance, are working toward a pan-European quantum network. Similar programs exist in the United States, Japan, South Korea, and India. The quantum hardware landscape is more varied than public coverage typically suggests. Most media attention focuses on superconducting qubit systems, which are what Google, IBM, and several startups, including Rigetti Computing, use. Superconducting qubits are artificial atoms made from electrical circuits cooled to temperatures near absolute zero, typically around 15 millikelvin, or about 15 thousandths of a degree above absolute zero. At these temperatures, the circuits become superconducting, meaning they carry electrical current with zero resistance, and quantum effects dominate their behavior. These systems have several advantages. They can be fabricated using existing semiconductor manufacturing techniques. They operate at high speeds, and they are relatively well understood. The main disadvantage is the extreme cooling required and the relatively short coherence times the time a qubit can maintain its quantum state before decoherence destroys it. Trapped ion systems use a completely different approach. Individual ions, atoms that have been given an electric charge by removing one electron, are suspended in a vacuum using electromagnetic fields and cooled with lasers to near absolute zero. The quantum states of interest are encoded in the electronic or nuclear spin states of the ions. Trapped ion qubits have significantly longer coherence times than superconducting qubits and can achieve very high fidelity operations. The main disadvantages are slower operation speeds and difficulty scaling to large numbers of ions while maintaining individual control over each one. Companies including IonQ and Quantinuum are leading commercial development of trapped ion quantum computers. Photonic quantum computing encodes quantum information in photons, particles of light. Photons are natural candidates for quantum information carriers because they interact weakly with their environment, which means they maintain quantum coherence easily. They are also natural carriers for quantum communication because they travel at the speed of light through fiber optic cables or free space. The challenge is that photons are hard to make interact with each other, which is necessary for the entangling operations that give quantum computers their power. Linear optical approaches use beam splitters and detectors to create probabilistic entangling gates, while other approaches use matter-based systems to mediate photon-photon interactions. PsiQuantum, Xanadu, and several other companies are pursuing photonic quantum computing. Topological qubits are perhaps the most exotic approach. The idea is to encode quantum information in collective quantum states of many particles that are topologically protected, meaning small, local perturbations cannot destroy the quantum information because the information is stored in a global property of the system rather than any local feature. This would dramatically reduce the overhead needed for error correction. Microsoft has been pursuing topological qubits using exotic quasi-particles called Majorana fermions for many years. Progress has been slow but continues. In 2023, Microsoft announced progress in demonstrating the basic physical behavior needed for topological qubits, though a practical topological quantum computer remains in the future. Neutral atom quantum computers use individual neutral atoms trapped in arrays of tightly focused laser beams called optical tweezers. The atoms can be arranged in arbitrary, two-dimensional or three-dimensional configurations, and their quantum states manipulated using laser pulses. This approach has shown rapid progress recently, with demonstrations of systems containing hundreds of qubits with high connectivity and low error rates. Companies including Quera and Pascal are developing neutral atom systems. Each of these hardware approaches has its own error mechanisms, its own strengths in terms of connectivity and gate fidelity, and its own path to scalability. It is not yet clear which approach or combination of approaches will prove most successful for large-scale quantum computing. The diversity of approaches is actually a strength of the field. Different hardware may prove optimal for different applications, and advances in one platform often illuminate possibilities in others. The quantum software stack is also maturing. Programming a quantum computer requires a fundamentally different approach than programming a classical computer. Classical programs are sequences of instructions that modify the states of bits. Quantum programs, quantum circuits, are sequences of quantum gate operations that manipulate qubits, transform their superpositions, create entanglement, and ultimately produce measurements. Designing quantum algorithms requires understanding quantum mechanics deeply enough to engineer specific interference patterns that will amplify correct answers while suppressing incorrect ones. Several quantum programming languages and software frameworks have been developed. Qiskit, developed by IBM, is an open-source Python library for writing and executing quantum circuits. Cirq, from Google, serves a similar purpose. PennyLane, from Xanadu, is designed specifically for quantum machine learning applications. These tools abstract away the hardware-specific details and allow researchers and developers to write quantum programs that can, in principle, run on multiple hardware platforms. Quantum algorithms research is producing new results regularly. Beyond Shor's algorithm for factorization and Grover's algorithm for unstructured search, which was the first quantum algorithm demonstrated to provide a provable speedup over all classical algorithms for a specific problem class, researchers have identified quantum advantages for linear algebra, optimization, simulation, and machine learning. The boundaries of what quantum computers can and cannot do efficiently are being mapped out through a combination of new algorithm discoveries and new complexity theoretic lower bounds. Quantum complexity theory, the study of what problems can be efficiently solved on quantum computers, has identified several complexity classes relevant to understanding quantum advantage. The class BQP, for bounded error quantum polynomial time, contains all problems solvable efficiently by a quantum computer. It is known to contain the factoring problem, which is the basis of Shor's algorithm's importance, and to contain problems in a class called BPP, which is the classical probabilistic analog. Whether BQP contains problems that are no problem complete, the class of problems that classical computers are believed unable to solve efficiently, is an open question, with significant implications for cryptography and computational complexity theory. The practical development of quantum computing is also driving advances in classical computing and computer science more broadly. The study of quantum error correction has led to new ideas in classical error correction and coding theory. The development of quantum algorithms has illuminated the structure of classical algorithms and the nature of computational complexity. The engineering of quantum hardware has pushed the boundaries of materials, science, cryogenic engineering, and precision measurement. One particularly striking example is quantum sensing. The same quantum mechanical properties that make qubits delicate, their extreme sensitivity to environmental perturbations, can be harnessed for ultra-precise measurement. Quantum sensors exploiting superposition and entanglement can measure magnetic fields, gravitational fields, acceleration, time, and temperature with precision far beyond classical instruments. Quantum magnetometers can detect the magnetic field of a beating human heart from outside the body. Quantum gravimeters can map subsurface geology with exquisite precision. Quantum clocks, optical atomic clocks, are so precise that they would not gain or lose a second over the age of the universe. These quantum sensing applications are in some ways closer to practical deployment than large-scale quantum computing. They do not require millions of error-corrected qubits. They require carefully controlled quantum states of a few atoms or photons, which is challenging but achievable with current technology. Quantum sensors are being deployed for medical imaging, geological surveying, navigation, and fundamental physics experiments. The intersection of quantum computing with fundamental physics experiments is particularly exciting. The Large Hadron Collider at CERN produces enormous quantities of data from particle collisions, and analyzing that data to identify rare events requires sophisticated computational approaches. Quantum machine learning algorithms are being explored for particle physics data analysis. Quantum simulations of field theories, the mathematical frameworks describing particle physics, could illuminate processes that are currently inaccessible to both theoretical calculation and classical simulation. Quantum computing also intersects with cosmology in ways that are just beginning to be explored. The cosmic microwave background, the afterglow of the Big Bang, still visible as faint microwave radiation from every direction in the sky, encodes information about the quantum fluctuations in the very early universe. These quantum fluctuations, which existed when the universe was a tiny fraction of a second old, are the seeds from which all cosmic structure, galaxies, clusters, filaments, eventually grew. Quantum computing could help model the early universe's quantum mechanical processes with a fidelity that classical computers cannot achieve. Dark matter and dark energy, which together constitute roughly 95% of the energy content of the universe, remain among the deepest mysteries in physics. Dark matter interacts gravitationally but does not emit light. Dark energy drives the accelerating expansion of the universe. Neither has been directly detected or identified. Quantum simulators might be able to model proposed dark matter candidates and their expected interactions, helping narrow the search. Quantum computing approaches to analyzing cosmological data sets might reveal patterns invisible to classical analysis. The possibility that quantum computing could help crack the problem of room temperature superconductivity is particularly tantalizing from an energy perspective. Superconductors materials that conduct electricity with zero resistance currently require cooling to very low temperatures, making them practical only in specific high-value applications like MRI machines and particle accelerators. A room temperature superconductor would revolutionize energy transmission and storage, potentially eliminating most of the energy lost to resistance in electrical grids. Finding such a material requires understanding quantum mechanical behavior of electrons in solids at a level of detail that quantum simulators are specifically designed to provide. Nuclear fusion, the process that powers the sun and all stars, is another application where quantum simulation could be transformative. Fusion reactions involve quantum mechanical processes among atomic nuclei at extreme temperatures and densities. Designing fusion reactors requires understanding plasma physics at a quantum level that classical simulation cannot fully capture. A practical fusion power plant would provide essentially limitless clean energy, and quantum computing could help solve the plasma physics challenges that have kept fusion power perpetually 20 years away for the past 60 years. These applications, drug discovery, materials design, fusion energy, cosmology, fundamental particle physics, represent the horizon of what quantum computing might eventually make possible. They are not science fiction. They are straightforward extrapolations from known physics and the capabilities that quantum computers are demonstrating at increasing scale. The question is not whether these applications are physically possible, it is whether the engineering can be made to work at sufficient scale. The national security implications extend beyond cryptography. Quantum computing could dramatically accelerate the design and simulation of complex systems relevant to defense, including materials for advanced military hardware, optimization of logistics and supply chains for military operations, and simulation of electromagnetic environments relevant to radar and communication. Governments are investing accordingly. The United States, China, the European Union, the United Kingdom, Japan, and India each have national quantum initiatives with funding measured in billions of dollars. The ethical dimensions of quantum computing are not merely about what the technology can do, but about who controls it and who benefits. If quantum computers become powerful enough to break current encryption before quantum-resistant alternatives are fully deployed, the transition period creates a window of vulnerability that could be exploited by any actor, state, or non-state that achieves quantum computational capability before the rest of the world has updated its security. Infrastructure. Managing this transition equitably and ensuring that the most sensitive communications of individuals, corporations, and governments are protected throughout requires international cooperation of a kind that is currently not fully in place. More broadly, the transformative potential of quantum computing in drug discovery and materials design will not automatically be distributed equally. The institutions best positioned to exploit early quantum computing advantages are large pharmaceutical companies, major financial institutions, and governments with substantial research budgets. Ensuring that the benefits of quantum computing contribute to global health, clean energy, and economic development rather than concentrating advantage in already powerful hands is a governance challenge that does not have a technical solution. This is not a reason to slow the science, but it is a reason to think carefully as the technology matures about how its benefits are structured and who is included in decisions about its deployment. Return one final time to the philosophical core of what quantum computing reveals. We live in a universe where the most fundamental description of physical reality is probabilistic, where particles do not have definite properties until they are measured, where distant objects can be correlated in ways that no classical mechanism can explain, and where the very act of measurement affects what is being measured. These facts are not philosophical positions that physicists have chosen to adopt. They are empirical discoveries, confirmed by experiment to extraordinary precision over nearly a century. Quantum mechanics tells us that the universe is not a machine running on hidden gears that we have not yet found. It is a structure in which certain questions do not have definite answers until they are asked, and the asking changes the answered. Quantum computers do not transcend these facts, they implement them. A quantum computer is a device that allows us to harness the genuine indeterminacy, the genuine entanglement, and the genuine superposition of the physical world, and direct them toward computation. In doing so, they do not make quantum mechanics more familiar or intuitive. They make its strangeness directly useful. What remains at the frontier of understanding is whether quantum mechanics is itself the final word or merely a stepping stone to something deeper. The incompatibility between quantum mechanics and general relativity, between the physics of the very small and the physics of the very large, suggests that both theories are approximations to some more fundamental framework that no one yet knows how to write down. String theory, loop quantum gravity, causal set theory, and other approaches to quantum gravity each attempt to find that deeper framework, but none has yet succeeded in making definitive experimental predictions that could distinguish it from the alternatives. Quantum computers may be essential tools in this search. The wormhole simulation on Sycamore is an early example of using quantum hardware to probe the deep structure of spacetime. As quantum computers become more powerful, they will enable more sophisticated explorations of quantum gravity scenarios, holographic dualities, and the emergence of spacetime from quantum information. The question of whether space and time are fundamental or derived from something more basic may ultimately be answerable only by experiment, and the experiments may require quantum computers. We are at an unusual moment in the history of science. The technologies we are building are revealing the depths of what we do not yet understand. Every advance in quantum computing raises new questions about the nature of quantum information, the structure of space-time, and the limits of computational knowledge. The field is not approaching completion, it is discovering how much further there is to go. This is exactly where science should be. Not at the end of a story, but at the beginning of a chapter whose contents are not yet written. There is a concept in mathematics called computational complexity that is worth understanding deeply because it illuminates not just the promise of quantum computing, but the nature of difficulty itself. Problems in computation are classified by how their difficulty scales with their size. Some problems are easy in the sense that doubling the size of the input only doubles the time needed to solve it linear scaling. Others scale quadratically, double the input size, and the time required roughly quadruples. These are all polynomial time algorithms, and problems solvable by polynomial time algorithms are considered computationally tractable regardless of the specific polynomial exponent. Then there are the hard problems. Integer factorization, the mathematical problem that RSA encryption relies on, is believed to require time that grows exponentially with the size of the number being factored on any classical computer. Exponential growth means that if factoring a 100-digit number takes a certain amount of time, factoring a 200-digit number takes not twice as long, but vastly, incomprehensibly longer. This is the mathematical cliff that makes RSA encryption secure on classical hardware. The class of problems called no problem contains problems whose solutions can be verified quickly, even when finding those solutions is hard. The traveling salesman problem, finding the shortest route, visiting a collection of cities, is no problem. Satisfying a complex logical formula is no problem. Packing objects of irregular sizes into a container optimally is no problem. These are problems with enormous practical importance. The existence of fast quantum algorithms for no-problem complete problems would be a revolution not just for computing, but for mathematics, logistics, drug design, and essentially every field that involves optimization. Whether quantum computers can solve no-problem complete problems efficiently is one of the great open questions in theoretical computer science. The current state of knowledge suggests probably not the class of problems efficiently solvable by quantum computers appears to contain factoring and certain other specific problems, but not the full class of no-problem complete problems. This is an active research area with significant implications. What quantum computers definitively can do is solve certain problems outside no problem in polynomial time. Simulating quantum systems accurately is one such problem. It is believed to be outside no problem for classical computers, meaning even verifying classical solutions efficiently is hard. But quantum computers can simulate quantum systems directly in polynomial time. This is arguably the most well-established and scientifically fundamental quantum advantage. The concept of quantum supremacy or quantum advantage is also worth examining carefully, because the terminology has been used in ways that sometimes obscure more than they reveal. When Google claimed quantum supremacy in 2019 with the Sycamore processor, the claim was that Sycamore had performed a specific computation in 200 seconds that would have taken the world's fastest classical supercomputer 10,000 years. This is not a claim that quantum computers are now generally more powerful than classical computers. It is a claim that for one specific type of computation sampling from the output distribution of a random quantum circuit, the quantum hardware is dramatically faster. IBM disputed the timescale, arguing that optimized classical algorithms could do the same computation in about 2.5 days rather than 10,000 years. But even 2.5 days versus 200 seconds is a meaningful quantum advantage for that specific task. The debate was less about whether quantum computers can outperform classical hardware on specific tasks, and more about how large and practically significant the advantage is for various tasks. The calculation of exactly when quantum computers will achieve a practically significant advantage on problems of commercial or scientific value, as opposed to benchmark computations specifically designed to showcase quantum hardware, is genuinely uncertain. IBM's roadmap has targeted practical quantum advantage within a few years. Google's research suggests similar timescales. Independent analysts are more cautious. The truth is that it depends heavily on what problem you choose, what algorithmic optimizations classical computers can deploy, and what level of quantum error correction becomes feasible at each stage of hardware development. What is not uncertain is the trajectory. The qubit counts in leading systems have grown dramatically over the past decade. Error rates have declined, coherence times have extended. The theoretical tools for quantum algorithm design have become more sophisticated. The engineering infrastructure for building, controlling, and characterizing quantum hardware has matured. The field is not stagnating. It is advancing on multiple fronts simultaneously. One particularly important area of progress is quantum error mitigation, which is distinct from quantum error correction. Error correction uses redundancy encoding logical qubits in many physical qubits to actively detect and fix errors. Error mitigation uses classical post-processing of quantum measurements to reduce the impact of errors without eliminating them. This approach is more limited than full error correction, but requires far fewer physical qubits and is practical with current hardware. Several techniques, including zero-noise extrapolation, probabilistic error cancellation, and symmetry verification, have been demonstrated to significantly improve the accuracy of quantum computations on noisy hardware. The near-term regime of quantum computing, before full fault-tolerant quantum computers are available, is often called NISQ, for Noisy Intermediate Scale Quantum. NISQ devices have tens to a few hundred qubits, with error rates that are manageable for short computations but accumulate over longer circuits. Understanding what computationally useful tasks NISQ devices can perform is one of the central questions of current quantum computing research. Variational quantum algorithms, which combine quantum hardware with classical optimization loops, are one of the most promising approaches for NISQ devices. In a variational quantum algorithm, a quantum circuit with adjustable parameters is run on the quantum hardware, producing some output that is fed into a classical optimization algorithm, which adjusts the parameters and runs the circuit again. This hybrid approach can leverage quantum superposition and entanglement for the parts of the computation where quantum hardware provides advantage, while using classical hardware for the optimization steps where classical computers excel. Variational quantum eigensolvers for chemistry simulation and quantum approximate optimization algorithms for combinatorial optimization are the most studied examples. The practical performance of variational algorithms on current hardware is an area of active investigation and some controversy. Several studies have shown that carefully optimized classical algorithms can match or exceed the performance of variational quantum algorithms on problems small enough to be handled by current quantum hardware. Whether this pattern will persist as hardware improves and problem sizes grow is not yet known. The optimistic view is that variational quantum algorithms will prove genuinely advantageous for quantum chemistry and optimization at scales beyond classical reach. The pessimistic view is that the noise in current hardware fundamentally limits variational algorithm performance in ways that will not be fully overcome until fault-tolerant qubits are available. Regardless of which view proves correct for near-term hardware, the long-term case for quantum computing on fault-tolerant hardware rests on provably exponential separations between quantum and classical computational complexity for specific problem classes. Quantum simulation of chemistry and materials, in particular, has a theoretical basis that does not depend on hardware, noise, or algorithmic heuristics. It rests on the fundamental physics of quantum mechanics. The systems being simulated are themselves quantum mechanical, and quantum computers can represent and evolve quantum states with exponentially less overhead than classical computers can. The scale of molecular simulation needed for drug discovery gives a sense of the challenge and the opportunity. Current computational drug discovery uses classical molecular dynamics, simulations, and quantum chemistry calculations that are limited to relatively small molecules and approximate force fields. These methods are powerful and have contributed to many drug approvals, but they miss the detailed quantum mechanical effects that can determine whether a drug candidate will bind to its target protein, how it will be metabolized in the body, and whether it will cause off-target effects that produce side effects. Full quantum mechanical simulation of even moderately sized drug molecules and their protein targets would require quantum hardware at a scale well beyond current capability, but within the theoretical roadmap of fault-tolerant quantum computing. The timeline for achieving this scale of quantum simulation is typically estimated at 10 to 20 years by leading researchers, though the uncertainty is large enough that earlier or later timelines cannot be excluded. The specific milestones on the path achieving error rates below the threshold for fault-tolerant operation, implementing logical qubits using surface codes or other error-correcting codes, scaling logical qubit counts while maintaining fidelity are technically demanding but well-defined. Progress on each milestone is measurable and has been achieved incrementally over the past decade. Quantum computing also has potential to accelerate the development of new quantum computing hardware through a kind of bootstrapping. Quantum systems that are difficult to simulate classically could be used to test and characterize quantum hardware components, potentially enabling the development of better hardware than could be designed using purely classical tools. The relationship between quantum computing and climate science is worth examining. Climate models require simulating the interactions of molecules in the atmosphere, the behavior of ocean currents, the dynamics of ice sheets, and the complex feedback loops connecting these systems. The quantum mechanical processes that determine how greenhouse gases absorb and re-emit infrared radiation, how aerosols affect cloud formation, and how chemical reactions in the atmosphere proceed, are all in principle accessible to quantum simulation. Classical models approximate these processes using parameterizations, simplified representations that capture average behavior but lose detail. Quantum simulation could replace these approximations with first principles calculations, potentially improving the accuracy of climate projections at exactly the scales where the approximations currently introduce the most uncertainty. The energy demands of quantum computing hardware are also relevant to climate considerations. Current superconducting quantum computers require cooling to millikelvin temperatures using dilution refrigerators that consume significant electrical power. As quantum computing scales, these energy demands will scale as well. The development of more energy-efficient quantum hardware, including approaches that can operate at higher temperatures or use less power for cooling, is an active area of research. Room temperature quantum computing would be transformative in terms of energy efficiency and practical accessibility, but current understanding of decoherence does not suggest a near-term path to room temperature operation for most qubit types. Photonic qubits, which naturally operate at room temperature and do not require cooling, are one exception, though they face other engineering challenges. The economic analysis of quantum computing development provides useful context. The global investment in quantum technology, spanning quantum computing, quantum communication, and quantum sensing, has grown rapidly, reaching tens of billions of dollars annually by the mid-2020s. The majority of this investment comes from national governments, with the United States, China, and the European Union each committing multi-billion-dollar programs. Private investment from technology companies including Google, IBM, Microsoft, Amazon, and many startups has added to this total. The return on this investment will not be uniform across application domains. Some applications, quantum communication and quantum sensing, are already generating economic returns because they do not require fault-tolerant, large-scale quantum computers. Quantum key distribution systems are being sold commercially. Quantum sensors are deployed in research and some commercial applications. These early commercial applications are helping to fund the longer-term development of fault-tolerant quantum computing. The timeline to economic return from fault-tolerant quantum computing is harder to estimate. The most valuable applications breaking current encryption, simulating large drug molecules, optimizing complex logistical networks, require a level of quantum capability that does not yet exist. But the potential economic value of these applications, if achieved, is enormous. A quantum computer that could simulate protein folding and molecular interactions accurately enough to dramatically accelerate drug discovery could be worth hundreds of billions of dollars in reduced development costs and faster time to market for new therapies. The workforce implications of quantum computing are beginning to be felt. Quantum computing requires expertise in quantum physics, computer science, mathematics, and engineering, a combination that relatively few people currently possess. Universities around the world are expanding quantum-focused educational programs. Companies are investing in training and are competing intensely for the limited pool of qualified researchers and engineers. This talent shortage is one of the practical constraints on how quickly the field can advance. Quantum computing literacy. The ability to understand at a conceptual level what quantum computers can and cannot do is increasingly relevant for decision makers in industry, government, and academia who are not themselves quantum physicists. The next decade will bring quantum computing capability closer to practical relevance for a wider range of problems, and the leaders of organizations in those domains will need to understand enough to make informed decisions about when and how to engage with quantum computing resources. This is part of why clear, accurate science communication about quantum computing matters. The field is surrounded by both excessive hype claims that quantum computers will solve all computational problems, or that they are already transforming industry and dismissive skepticism that underestimates the genuine theoretical foundations and the real progress being made. Neither extreme is accurate. Quantum computing is a field with profound theoretical underpinnings, significant engineering challenges, genuine progress on those challenges, and a realistic, if uncertain, path to transformative, practical capability. The scientific community working on quantum computing is aware of both the promise and the limitations. Publications in leading journals like Nature, Science, and Physical Review Letters regularly report advances in qubit coherence times, gate fidelities, error correction protocols, and algorithm development, alongside clear-eyed assessments of what remains to be accomplished. The discourse within the field is substantially more nuanced than what typically reaches public attention. One aspect of quantum computing that rarely receives attention but is scientifically fundamental is the connection to thermodynamics. Computation is not free, it requires energy. The laws of thermodynamics apply to quantum computation just as they apply to everything else. Landauer's principle establishes that erasing a bit of information going from a known 1 to a known 0 requires dissipating a minimum amount of energy as heat. This principle connects information theory to thermodynamics and sets a fundamental lower bound on the energy cost of computation. Quantum computing does not escape thermodynamics. Quantum measurements, which are necessary to extract results from a quantum computation, are irreversible processes that dissipate energy. The cooling of quantum hardware to millikelvin temperatures is itself a thermodynamic process that requires energy. Understanding the thermodynamics of quantum computation, how much energy is fundamentally required, how much is wasted by current hardware, and how close to the thermodynamic limits future hardware might come, is an active area of research with implications for both the practical energy efficiency of quantum computers and fundamental physics. Maxwell's demon, a thought experiment proposed in the 19th century in which a hypothetical demon appears to violate the second law of thermodynamics by selectively opening a door between two chambers based on the speeds of individual molecules, is resolved by recognizing that the demon's memory of which molecules it has observed must eventually be erased, and that erasure costs energy. This resolution, developed by Leo Szilard and later Rolf Landauer, connects the physics of information directly to thermodynamics. Quantum computers, which process information in fundamentally new ways, raise new questions about the relationship between computation and thermodynamics that are still being worked out. The measurement problem in quantum mechanics, the question of why and how quantum superpositions collapse into definite outcomes when measurements are made, is relevant to quantum computing in a practical way. Every quantum computation ends with a measurement that collapses the quantum state into a classical outcome. The theory of quantum mechanics provides the probabilities for different outcomes, but does not explain why a specific outcome occurs in any given run. This is not just a philosophical puzzle. It has practical implications for how quantum algorithms are designed and how results are interpreted. Different interpretations of quantum mechanics, the Copenhagen interpretation, the many worlds interpretation, the pilot wave interpretation, and others agree on the predictions but disagree about what is really happening physically. These interpretational differences do not affect the predictions of quantum mechanics, and therefore do not affect the design or operation of quantum computers. But they do affect how we conceptualize what quantum computation means, whether the parallel computations in superposition are happening in genuinely distinct parallel realities, whether the wave function represents our knowledge or physical reality, and what it means for a quantum computer to find the correct answer among many simultaneous possibilities. The many worlds interpretation, associated with Hugh Everett III, who proposed it in 1957, is particularly interesting in this context. According to many worlds, When a quantum computation proceeds and different branches of the wave function evolve separately, each branch is physically real. The computation genuinely explores multiple possibilities in multiple branches of reality simultaneously. The measurement at the end of the computation selects one branch from our perspective, while other branches continue to exist. In this view, quantum computers are not just faster classical computers. They are machines that leverage the branching structure of reality to perform computations across the multiverse. This is philosophically extraordinary and remains deeply contested. But it is worth noting that many worlds is taken seriously by a significant fraction of physicists, not as a certainty, but as a coherent interpretation that makes no additional assumptions beyond those already contained in the GRUs. Standard quantum mechanical formalism. Whether or not it is literally true, it provides an intuitively vivid way to understand why quantum computers can explore exponentially many possibilities simultaneously. Because, in a deep sense, they are. The future of quantum computing is inseparable from the future of our understanding of physics at its deepest level. As quantum computers become more capable, they will be used not just to solve specific practical problems, but to test fundamental physical theories, explore the boundaries of quantum mechanics, and probe the structure of spacetime in ways that no other tool can match. The history of science suggests that the most transformative advances often come not from directly solving a known problem, but from developing a new tool that reveals previously invisible aspects of reality. The telescope revealed that the night sky was not a fixed celestial dome, but an infinite expanse of stars and galaxies. The microscope revealed that living organisms were composed of cells and that diseases had physical causes in microorganisms. The particle accelerator revealed the substructure of protons and neutrons, and the existence of quarks and the Higgs boson. Quantum computers are the next instrument of this type, not just a faster way to compute, but a new way to probe the structure of the physical world. What they will reveal, we do not yet know. That is the nature of genuinely new instruments. They answer questions we knew how to ask, and they reveal questions we did not know we should be asking. The universe is patient. It has been running its quantum computation for nearly 14 billion years. We are only just beginning to learn how to listen. If the ideas in this exploration resonate with you, if the intersection of quantum physics, computation, and fundamental reality seems like something worth following, then staying curious, reading more, and engaging with the actual science rather than the hype is the most valuable thing you can do. The field will produce major announcements in the coming years. Some will be genuine milestones, some will be marketing. Knowing enough to distinguish between them is its own form of quantum advantage. Like and subscribe if you want to stay informed as quantum computing advances, because the next few years are going to be genuinely interesting. To close out this exploration properly, there is one more dimension worth adding, a dimension that does not appear in most discussions of quantum computing, but that may ultimately be the most significant. The question of what quantum computation tells us about the nature of knowledge itself. Science is a process of building models of reality. Those models are never the reality itself. They are representations, compressed, simplified, useful approximations that capture certain aspects of the world accurately enough to predict outcomes and guide action. Newtonian mechanics is a model. It works extraordinarily well at human scales and everyday velocities. It fails at very high speeds, very strong gravitational fields, and very small sizes. Special relativity replaces it for high speeds. General relativity replaces it near massive objects. Quantum mechanics replaces it at atomic scales. Each replacement preserves the successes of the previous model, while extending the domain of accurate prediction. This pattern suggests that our current best theories, quantum mechanics and general relativity, are themselves approximations to something more fundamental that we have not yet discovered. The evidence for this is precisely their mutual inconsistency. They cannot both be exactly right in all regimes because their mathematical structures are incompatible. The regime where both would need to apply simultaneously the very early universe, the interior of black holes, is a regime where our current theories give nonsensical answers like infinite density and infinite energy. Quantum gravity, the sought-for theory that would reconcile these two frameworks, would be the deepest layer of physical description we have yet achieved. It would describe reality at the Planck scale, a length scale of approximately 1.6 times 10 to the negative 35th meters, a density of approximately 5 times 10 to the 96th kilograms per cubic meter, a timescale of approximately 5.4 times 10 to the negative 44th seconds. These are not scales that any experiment currently probes directly. They are inferred from the mathematics of the theories. The prospect that quantum computers could help probe quantum gravity even indirectly through simulations of quantum field theories and holographic dualities is genuinely exciting to theoretical physicists. The wormhole experiment on Sycamore was a proof of concept. Quantum hardware can implement computations corresponding to quantum gravity scenarios and produce results consistent with theoretical predictions. As hardware scales, so does the potential complexity of the quantum gravity scenarios that can be explored. The holographic principle, which provided the theoretical framework for the wormhole experiment, is worth explaining more fully because it is one of the most profound ideas in contemporary theoretical physics. It was first proposed in the context of black hole thermodynamics by Jacob Bekenstein and Stephen Hawking in the 1970s. When an object falls into a black hole, what happens to the information it carries? Classical general relativity says it is simply absorbed into the black hole, and the black hole grows in mass. But quantum mechanics says information cannot be destroyed, it must be preserved somewhere in the evolution of the quantum state. This apparent contradiction is called the black hole information paradox. Hawking showed in 1974 that black holes emit thermal radiation, what is now called Hawking radiation, as a consequence of quantum effects near the event horizon. This radiation is thermal, meaning it carries no information about what fell into the black hole. If Hawking radiation is exactly thermal, and if the black hole eventually evaporates completely through this radiation, then all the information about what formed the black hole would be destroyed. This violates a fundamental principle of quantum mechanics called unitarity, the principle that quantum evolution is reversible and information is conserved. This paradox remained unresolved for decades. In the 1990s, Juan Maldacena discovered a remarkable mathematical relationship now called the anti-de Sitter conformal field theory correspondence, or ADS, CFT duality. This duality states that a theory of quantum gravity in a particular kind of spacetime, anti-de Sitter space, which has a specific geometry with negative curvature, is exactly equivalent to a quantum field theory without gravity, living on the lower dimensional boundary of that space. This is the holographic principle made precise. The physics of the bulk three-dimensional space, including all its gravitational dynamics, is completely encoded in the two-dimensional boundary theory. Nothing is lost, no information is hidden. The apparent three-dimensionality of the bulk is an emergent property of the two-dimensional boundary theory. ADS, CFT does not directly describe our universe, which does not have anti-de Sitter geometry. Our universe appears to have positive rather than negative curvature, and is expanding rather than being held in a fixed geometry. But ADS, CFT, provides a concrete mathematical framework in which questions about quantum gravity can be asked and answered, and it provides insight into what a theory of quantum gravity might look like in our universe. The resolution it suggests for the black hole information paradox is that information is not lost when it falls into a black hole. It is encoded on the boundary, the event horizon, in a scrambled form that eventually emerges in the Hawking radiation. The information is preserved, but the scrambling is so severe that extracting it from the Hawking radiation would require a quantum computation of mind-boggling complexity. This resolution is not universally accepted. There remain competing views, but it is currently the leading proposal. The connection between entanglement and spacetime geometry that the wormhole experiment tested is rooted in ADS-CFT. In the holographic framework, the entanglement between regions of the boundary theory corresponds to the connectivity of the bulk space. Regions of the boundary that are highly entangled correspond to regions of the bulk that are nearby. Regions that are not entangled correspond to regions of the bulk that are far apart or disconnected. In this picture, spacetime connectivity, the fact that space is a connected geometry with well-defined distances, emerges from the pattern of quantum entanglement in the boundary theory. This suggests something extraordinary. Space itself is not fundamental. It emerges from entanglement. The geometric structure of the universe, the fact that there is a space in which objects can be near or far, connected or disconnected, is a consequence of quantum information, relationships, rather than a given background on which events play out. If this is correct, it completely changes our conceptual picture of what the universe is. Space would be not the stage, but the story, not the background on which events happen, but itself an emergent phenomenon arising from more fundamental quantum information structure. This is a profound departure from every previous physical framework, including general relativity, which treats spacetime as the fundamental arena in which all physics occurs. Quantum computers, in this picture, are not just tools for computation, they are models of the fundamental structure of reality. When a quantum computer processes a state in superposition, it is implementing the same type of information processing that, at cosmic scales, gives rise to space itself. When entanglement is created between qubits, it mirrors the entanglement relationships that generate spatial connectivity in the holographic description of the universe. This is admittedly speculative. The holographic principle and ADS-CFT are theoretical frameworks, not established facts about our universe. The connection between entanglement and space-time geometry is a research program, not a completed theory. The interpretation of the wormhole experiment as evidence for these ideas requires significant theoretical assumptions that are actively debated, but the directionality of the evidence is striking. Multiple independent lines of theoretical physics converge on the idea that quantum information is more fundamental than space or time. Black hole thermodynamics, the holographic principle, ADS-CFT, the ER equals EPR conjecture, which proposes that entanglement between particles is equivalent to a quantum wormhole, connecting them all point in the same direction. They suggest that at the deepest level of physical description, the universe is made of quantum information, and space and time are features that emerge from the organization of that information. In this context, quantum computers are not just technologically significant. They are conceptually fundamental. They are the first systems that humans have built that operate according to the same principles that may generate the structure of spacetime itself. Building and understanding quantum computers may be, in a deep sense, learning to read the source code of the universe. The physicist John Archibald Wheeler, who worked closely with Niels Bohr and later with Richard Feynman, spent the final decades of his career developing the idea that he summarized in the phrase "it from bit," the proposal that every physical quantity, every aspect of the physical universe, derives its existence from information, from answers to yes or no questions. He later updated this to "it from qubit," acknowledging that the relevant information is quantum rather than classical. Wheeler's intuition was philosophical and not yet grounded in a precise theoretical framework. But the developments in holographic duality, the emergence of space from entanglement, and the experimental demonstrations of quantum information principles in physical systems like the Sycamore processor all move in the direction his intuition pointed. The universe may be, at its most fundamental level, a quantum information structure, and quantum computers may be the instruments through which we learn to read it. This leaves us with a remarkable situation. We are building machines that implement, in a controlled and useful way, the same principles that generate physical reality. We are using quantum computation to probe quantum gravity. We are using entanglement to simulate wormholes. We are using superposition to explore the exponentially vast space of possibilities that the universe itself navigates in producing every quantum outcome. The science is young. The hardware is rudimentary by the standards of what is theoretically possible. The algorithms are incomplete. The theoretical framework connecting quantum information to spacetime geometry is unfinished. But the direction is clear, and the questions are real. What is space made of? Where does time come from? How does the universe compute its own evolution? Why is there something rather than nothing? And is the something that there is fundamentally informational? These are not questions that quantum computers will answer alone. They are questions that require the combined efforts of theoretical physics, experimental physics, computer science, mathematics, and philosophy. But quantum computers are among the most powerful tools we have ever built for approaching these questions, and their continued development will expand what is knowable about the deepest structure of reality. That is the real significance of quantum computing. Not faster encryption breaking, not more efficient drug discovery, not better traffic routing, though all of those matter enormously for human welfare. The deepest significance is that quantum computers are instruments for interrogating the nature of reality itself, using the language that reality appears to be written in. We are at the beginning of this interrogation. The questions are harder and more interesting than they appeared to be. The tools are new and getting better. The universe has been patiently computing since the beginning, and we are only now learning enough of its language to start asking it questions it can answer. The answers, when they come, will be worth waiting for. There is something fitting about the fact that quantum mechanics, a theory built on probability, uncertainty, and the impossibility of complete knowledge, is the foundation of the most powerful computational tools we have ever conceived. Classical computing was built on the assumption that the universe is deterministic, that perfect information would yield perfect prediction, that the universe is a clock whose ticking could be precisely described and exploited. Quantum mechanics demolished that assumption. And yet, it is precisely the indeterminacy of quantum mechanics, its refusal to be pinned down to classical states, that gives quantum computers their power. This is not an accident. It is a deep feature of how the universe is organized. The uncertainty is not a flaw in our description. It is a feature of reality itself, and it is the same feature that makes exponentially large state spaces computationally accessible. The universe is uncertain in a way that is also, when properly harnessed, extraordinarily powerful. Heisenberg's uncertainty principle is usually presented as a limitation. You cannot know both the position and momentum of a particle with arbitrary precision. This is true. But the flip side is that a particle in a state of position uncertainty carries momentum, information, and vice versa. The uncertainty is not just a gap in knowledge. It is a genuine physical property that carries information about complementary quantities. Quantum computers exploit exactly this. The information contained in quantum uncertainty can be processed, transformed, and read out in ways that have no classical analog. The concept of quantum coherence, the maintenance of superposition over time, is similarly a property that appears as fragility from one perspective and as resource from another. Qubits decohere when they interact with their environment. This is a genuine challenge. But the coherence itself, while it lasts, is what makes quantum computation possible. The effort to maintain coherence for longer, across more qubits, at higher fidelity, is the central engineering challenge of quantum computing, and it is an effort to preserve a physical property that is genuinely extraordinary when it exists. There is a lesson here about the relationship between physical constraints and technological opportunity. Every major wave of technology has been built by taking a physical phenomenon that initially appeared as a limitation or a curiosity and learning to control and harness it precisely enough to use it as a resource. Electricity was initially a laboratory curiosity, dangerous, mysterious, and hard to control. Harnessing it required developing insulation, generation, transmission, and the theory of electromagnetism. Nuclear reactions were initially only observed in natural phenomena and understood theoretically. Harnessing them required solving enormous engineering and physics problems. Quantum effects tunneling, superposition, entanglement, interference are the next physical phenomena being harnessed, and the engineering required to control them is correspondingly demanding. The timescale of technological development, from laboratory curiosity to world-changing technology, has varied enormously across different technologies. The laser was invented in 1960 and was described at the time as a solution looking for a problem. Today, lasers are in every smartphone, every fiber optic cable, every barcode scanner, every DVD player, and every eye surgery clinic. The internet was a small academic network for the first 2 decades of its existence, and then transformed global civilization within another decade. The gap between scientific demonstration and pervasive technological deployment can be long or short, and it depends on factors economic, regulatory, cultural, and scientific that are difficult to predict. Quantum computing has been in the laboratory curiosity phase for several decades. The transition to the engineering phase, characterized by systematic, funded, competitive development of practical hardware and software, began in earnest in the 2010s and accelerated dramatically in the 2020s. The transition to the world-changing technology phase, when quantum computers are solving practically important problems that classical computers cannot, is not yet complete, but is closer than it has ever been. The intermediate stages are already producing value. Quantum key distribution is deployed commercially. Quantum sensors are in use in research and some industrial applications. Quantum simulation is producing results in condensed matter physics and quantum chemistry that advance scientific understanding, even if they do not yet replace classical approaches for practical applications. The quantum computing workforce is growing, and the training it requires is building expertise in quantum physics, quantum information theory, and quantum algorithm design that will be valuable across many decades. One dimension of quantum computing that is easy to underestimate is the role of mathematical insight versus hardware progress. Some of the most significant breakthroughs in quantum computing's potential have come not from building better hardware, but from discovering new algorithms. Shor's algorithm was a theoretical breakthrough that changed the perceived significance of quantum computing overnight. Grover's algorithm was another theoretical breakthrough that showed quantum speedup for a completely different class of problems. The discovery of new quantum algorithms with practical applications would have an impact comparable to these historical examples, regardless of the current state of hardware. Quantum algorithm discovery is, to some extent, constrained by the difficulty of the mathematics. Designing a quantum algorithm that provably outperforms all classical algorithms for a given problem requires proving lower bounds on classical computation, showing that no classical algorithm can do better, as well as constructing the quantum algorithm itself. Proving computational lower bounds is one of the hardest problems in theoretical computer science. The mathematical techniques required are subtle, and progress is slow. But each new result, each new quantum algorithm, each new lower bound that quantifies classical limitations builds the theoretical foundation for the field. The interaction between quantum algorithm development and complexity theory is bidirectional. Understanding what quantum computers can and cannot do efficiently requires understanding the structure of computational problems in detail. This understanding is advancing quantum computing research, while also advancing our basic knowledge of the mathematics of computation. The P versus no problem, whether every problem whose solution can be quickly verified can also be quickly solved, is one of the 7 Millennium Prize problems in mathematics, with a prize of $1 million for a solution. The quantum computing analog of this question is whether BQP equals no problem, and understanding the relationship between these complexity classes is a central question in theoretical computer science that quantum computing research is illuminating. The physical implementation of quantum error correction is worth examining in more detail because it is the central engineering bottleneck for fault-tolerant quantum computing. And understanding it clarifies the nature of the fault challenge. The simplest quantum error correcting code uses 3 physical qubits to encode 1 logical qubit. If one of the 3 physical qubits undergoes a bit flip error, the other 2 can be used to detect and correct the error through a majority vote, implemented using quantum measurements that detect errors without revealing the logical qubit state. This 3-qubit code corrects single-bit flip errors but not phase flip errors, a different type of quantum error with no classical analog. More sophisticated codes are needed to correct all types of quantum errors. The surface code, which is one of the leading candidates for practical fault-tolerant quantum computing, encodes 1 logical qubit in a 2-dimensional array of physical qubits arranged on a surface using checks between neighboring qubits to detect both bit flip and phase flip errors. The overhead, the number of physical qubits required per logical qubit, depends on the error rate of the physical qubits and the desired error rate of the logical qubit. For physical qubit error rates near current state-of-the-art, the surface code requires hundreds to thousands of physical qubits per logical qubit. Achieving the error rates needed for fault-tolerant computation with the surface code requires physical qubit error rates below approximately 1% and preferably below 0.1%. Leading quantum computing platforms have achieved gate error rates of fractions of a percent in controlled conditions, putting them near but not yet clearly below the fault tolerance threshold. The Willow processor's demonstration that adding more physical qubits can reduce the logical error rate rather than increasing it, as had been the case with earlier hardware, is the first clear experimental demonstration of crossing below the error correction threshold in a meaningful sense. The path from current hardware to fault-tolerant quantum computing is characterized by 3 parallel requirements. Physical qubit error rates must continue to decrease. The number of physical qubits must increase to support the overhead of error correction, and the classical control systems that coordinate quantum operations must scale in both speed and complexity to match the quantum hardware. All 3 are active engineering challenges, and progress on each is interdependent. More qubits at the same error rate enables longer computations, but requires more classical control overhead. Lower error rates at the same qubit count enable deeper circuits, but require more precise physical implementation. The development of quantum computing hardware is also driving progress in adjacent fields. Precision manufacturing at the nanoscale, required for superconducting qubit fabrication, is advancing the state-of-the-art in semiconductor manufacturing beyond what classical computing applications alone would demand. Cryogenic engineering, required for operating superconducting qubits, is advancing the technology of ultra-low temperature refrigeration. Precision laser systems, required for trapped ion and neutral atom quantum computers, are advancing optical engineering. Quantum computing is acting as a technology driver across multiple fields, not just as a consumer of existing technology. The international dimension of quantum computing development deserves more attention than it typically receives. The field is not organized as a unified global scientific enterprise in the way that particle physics is organized through CERN or astronomy is organized through large international telescope collaborations. It is instead a set of overlapping national and corporate efforts, competing on hardware benchmarks and algorithm demonstrations, with some scientific collaboration and significant strategic competition. China has invested heavily in quantum communication, with the Michus satellite and a growing ground-based quantum network, and in quantum computing hardware. The Chinese government views quantum technology as a strategic priority for national security and economic competitiveness. The United States has responded with the National Quantum Initiative Act, which established a multi-agency coordination structure for quantum research and allocated substantial federal funding. The European Union's Quantum Flagship Programme represents a similar multi-billion-dollar commitment across member states. The strategic competition is particularly acute in quantum communication, where quantum key distribution networks could provide communication security that is physically impossible to compromise, and in the potential to develop quantum computers capable of breaking current encryption. The first nation to achieve cryptographically relevant quantum computing capability would have a significant intelligence advantage: the ability to decrypt adversaries' encrypted communications while deploying quantum-safe encryption to protect its own. This is why the transition to post-quantum cryptography is treated as a national security issue rather than merely a technical upgrade. The mathematical foundations of post-quantum cryptographic systems, including lattice-based cryptography, hash-based cryptography, and code-based cryptography, are designed to be hard for quantum computers to break, using mathematical problems that do not yield to quantum speedup the way integer factorization does. Deploying these systems requires updating not just software, but hardware, protocols, and the entire ecosystem of digital certificates that underpin internet security. The migration to post-quantum cryptography is the largest coordinated change in internet security infrastructure in the history of the internet. It is not a single event, but a decade-long process that will require updating essentially every device and system that performs secure communications. The urgency is not because quantum computers capable of breaking current encryption exist today, they do not, but because the time required to complete the migration is long and the transition needs to begin well before the capability arrives. The cultural and philosophical impact of quantum computing may ultimately be as significant as its practical applications. The ideas that quantum mechanics forces on us the impossibility of perfect knowledge, the reality of superposition, the non-locality of entanglement, the emergence of space from quantum information are not just technical facts about small systems. They are facts about the fundamental structure of reality that challenge deep intuitions about what the world is and how it works. Popular culture has so far engaged with quantum computing, primarily through the lens of computing power quantum computers as super-fast machines that can break any code. This is an impoverished representation. The deeper story is about the nature of information, the structure of space, and the computational character of the universe itself. Making this story accessible, helping people understand not just what quantum computers can do, but what they reveal about the physical world, is a worthwhile goal for science communication. If you have stayed with this exploration to its end, you have encountered ideas that are genuinely at the frontier of human knowledge. Not summaries of settled science, but active research questions. Does spacetime emerge from entanglement? Is the universe fundamentally computational? What is the deepest description of physical reality? What are the limits of what can be known and computed? These questions matter because they define the frontier of understanding. Every generation inherits a set of answered questions and a set of open questions. The open questions of today include some that have been open since the dawn of modern physics, and others that have only become clearly formulable in the past few decades. Quantum computing sits at the intersection of several of these open questions, which is part of what makes it so intellectually exciting. The quantum age is beginning. It will not arrive all at once. It will arrive in stages, as hardware improves, as algorithms advance, as applications are demonstrated, as infrastructure is built. Some stages will be announced with fanfare and not immediately deliver on their promise. Others will quietly transform specific fields long before the transformation is widely recognized. Paying attention to the actual science, the peer-reviewed results, the honest assessments of capability and timeline, the theoretical advances alongside the engineering achievements is the best way to track this transformation accurately. The universe has been quantum mechanical since its first moments. We are just catching up.